to Unit 8.5. This is lesson number 5. We're still doing percent yield problems. Previously, you learned how to calculate percent yield with the basic formula being the actual yield divided by the theoretical yield multiplied by 100 to put it into percent form. We started by giving you the values for the actual yield and the values for theoretical yield. In just the last video lesson, lesson number 4, we learned that the theoretical yield can be determined using stoichiometric calculations. In this lesson, what we're going to do is figure out, well, what if you actually did the lab and you collected the data? How do you determine the actual yield from your data and then divide that by the stoichiometric theoretical yield? So we're putting all the pieces together for percent yield in this video lesson. So we have a chemical reaction where copper reacts with aqueous silver nitrate, AgNO3. After the reaction stopped, some copper was left over, which means the silver nitrate was used up completely and is considered what is called the limiting reactant. The products of the reaction are aqueous copper 2 nitrate, it's blue, and silver crystals. Here's the balanced equation, so it has a ratio of 1 to 2 to 1 to 2. And we have a data table here. The empty beaker weighs 93.80 grams. The mass of the beaker and the silver nitrate, I'm going to put the formula here, the silver nitrate, that's what you're starting with, was 95.90 grams. And the mass of the beaker and the silver crystals, just the Ag, which is the product, weighs 94.95 grams. So the first thing we need to do is we're going to try to figure out our theoretical yield. All right, and since we know that the silver nitrate was used up completely, that's the substance we want to start with. We need to be assured that all of the silver nitrate was used up, and therefore we can base that number, we can base the calculation on that starting mass. Okay, so the theoretical yield of silver is dependent on the mass of the silver nitrate to begin with. And so that's why we're going to start with that first calculation. Calculate the mass of the silver nitrate used up. Okay, remember silver nitrate is the AgNO3. And this is not a challenging calculation. We know that we have a mass here, AgNO3, but that also includes the mass of the beaker. So in this calculation, we just have to subtract out the empty beaker mass. So 95.90 grams minus the empty beaker of 93.80 grams. And you could probably do this in your head, but let's go ahead and use the calculator. 95.9 minus 93.8. And we get 2.10. Remember, we're going to maintain our digits after our decimal. So this is the mass of the AgNO3 that this person started with in this experiment. So that number is going to be the mass that we're going to start our gram-to-gram stoichiometry calculation. Okay. So using our answer from part A, we're going to calculate the theoretical yield of silver, right? So basically, let me go up here. Sorry to move the paper around. But if we're starting with 2.10 grams of silver nitrate, the question is, how many grams of silver can that make, right? So this is a gram-to-gram stoichiometry problem, right? And so I'm going to start 2.10 grams of AgNO3. Remember, we always write the mathematical quantity, the unit, and the identity. Gram-to-gram stoichiometry has me canceling out grams of AgNO3 and converting to moles of AgNO3. So this is a molar mass. We'll have to do a little side calculation. Silver is 107.9. We've got 1 nitrogen coming in at 14.0. And we've got 3 oxygens coming in at 16.0. So So 3 times 16.0. So if I add all that up, 16 times 3 plus 14 plus 107.9, we get 169.9. So that is the molar mass of AgNO3. Continuing on our gram-to-gram stoichiometry problem, I'm now needing to cancel out moles of AgNO3, and I'm going to convert to moles of silver. So this is from the balanced equation. Moles of AgNO3, the coefficient was 2. Moles of silver, the coefficient is 2. So really, 2 over 2 is like 1 over 1. It's not anything that's going to mathematically change, but this fraction allows us to manipulate our units appropriately. So I'm going to put moles of Ag down here to cancel, and grams of Ag silver up top. And if you recall, we know that the molar mass of just silver is 107.9. We figured that out earlier. And so now, units that cancel, grams of AgNO3 cancel, moles of AgNO3 cancel, moles of Ag cancel, leaving us with grams of silver. So now it's just time for the calculator work. Right, I've got, make sure you can see this all, 2.1 divided by 169.9, multiply by 2, divide by 2, those are going to cancel out, so I don't need to do any calculator work there, times 107.9. Rounded to 3 significant figures, I get 1.33 grams of silver. That's my theoretical yield. All right. So, but we still need to, before we can do our percent yield calculation, we need to use the data table above to find the actual yield of silver. In other words, how much silver was actually produced. So the final number, 94.95, includes the mass of the silver, but it also includes the mass of the beaker. So we're going to have to subtract out the mass of the empty beaker. So this part C, we're going to take the mass of the beaker with the crystals, 94.95 grams. And I have to subtract out the mass of the empty beaker at 93.80 grams. And let's see, if we do this in the calculator, 94.95 minus 93.8. So we get 1.15 grams of silver is the actual yield. All right, so these previous problems, we have just calculated our actual yield from the data table and our theoretical yield from the stoichiometry. Let's put those together to find percent yield. So percent yield is our actual of 1.15 grams divided by our theoretical of 1.33 grams, multiply by 100, grams of course cancel, and our calculator 1.15 divided by 1.33, multiply by 100, and this is a pretty good percent yield, 86.5% yield. All right, there you have it. I believe the problem on the back is your problem set to try. Give that a shot, check your work, and I'll see you back in the classroom.